Okay, now I shouldn't have issues there.
So what are you doing?
I have 10 minutes before class. I was just stretching a little.
Well, I heard your computer going off, so that's what I was curious if you had class or what.
Yep. In 10 minutes.
All right.
For those already online, go ahead and give me some indication if you can hear me. A thumbs up or something, a reaction. Gotcha. Good. Just wanted to make certain that there wasn't an issue. Okay, it's that time of the day, so we're going to go ahead and get started with class. Today, what we're going to be doing is we're going to continue embarking upon our trek through stoichiometry. Basically, again, stoichiometry is a fancy word that is the mathematics associated with chemistry. Stoichiometry involves the use of a variety of conversion factors. Some of those conversion factors include the metric to metric conversions, the English to metric conversions, Avogadro's number, which you use if you're dealing with molecules, ions, or atoms. The molar mass, which you use if you're dealing with grams, and then mole-to-mole ratios. We've already discussed one form of mole-to-mole ratio, which is found in the formula of a compound. It specifically describes the number of moles of an element in 1 mole of compound, and that descriptor comes from the subscripts of that element in the compound. But on Wednesday and Friday of last week, we developed another mole-to-mole rate, another location to obtain a mole-to-mole ratio, and that is going to be in the balanced chemical reaction. When we look at the balanced chemical reaction, the coefficients of the compounds in the reaction are describing the mole-to-mole ratio. Between those compounds. So for example, if I were to balance out the chemical reaction of octane, the combustion of octane, like is used in our gasoline, it would be 2C8H18 plus 25 O2 goes to give 16 CO2 plus 18 H2O. We can describe this as 2 molecules of C8H18 to 25 molecules of oxygen, but it's more common to describe it as 2 moles of C8H18 to 25 moles of O2 to 16 moles of CO2 to 18 moles of H2O. So again, there is a second conversion factor that involves the mole-to-mole ratio, but that is going to come from the balanced chemical reaction. Specifically, it's coming from the coefficients that we develop in balancing that chemical reaction. And those coefficients, they can be used to describe molecules of each substance, but they also can be used to describe moles. And we're going to typically use it to describe moles. Any questions so far? Because what we're going to do is we're going to look at how this information can be used in example problems. So let's look at an example problem. Sodium metal burns in air according to the balanced reaction for Na plus O2 goes to make 2 Na2Os. How many moles of oxygen are needed to completely react with 9.5 grams of sodium? Now, just like before, when I was performing stoichiometric calculations, I will be performing these calculations and I will be highlighting where the information is coming from based off of what we are given and what we want to solve for. So what we were given is we were given 9.5 grams of sodium. What we were asked to solve for is moles of oxygen. And now, if you'll recall, we used to ask ourselves some questions. We're going to ask those same questions. The first question is, are the substances the same? And the answer to that question is no. We're talking about two different substances. Two different substances. Means we need a mole-to-mole ratio. And this one is going to specifically come from the coefficients of the balanced chemical equation, which according to this, for every 4 moles of sodium that react, we need 1 mole of oxygen. The next thing I'm going to look at is I'm going to look at what I was starting with. I'm starting with grams. Anytime we're starting with grams, that means that we're going to need the molar mass. The molar mass of sodium is 22.99 grams of sodium is equal to 1 mole of sodium. The last thing that we're looking for is we're looking for moles. And we actually have moles in a couple of different locations. Specifically, we have one up in our mole to mole ratio, so I'm not going to worry about finding a conversion factor for that one. So having developed the conversion factors, we're ready to start this problem. We're going to start with what we were given, which is the 9.5 grams of sodium. Our first conversion factor needs to have grams of sodium. And so we're going to use our molar mass. Of that conversion factor, the 22.99 grams of sodium must go in the denominator so that the unit and the substance will cancel out, leaving me moles of sodium for the numerator. But we weren't asked for moles of sodium. We were specifically asked for moles of oxygen. So we need a second conversion factor that allows us to convert from moles of sodium to moles of oxygen, and that's going to be our mole to mole ratio. Of that mole to mole ratio, the sodium will go in the denominator, while the mole of oxygen goes in the numerator. The reason we place the moles of sodium in the denominator is so that the unit and the substance would cancel out, leaving us moles of oxygen, which is what we were asked to solve for. So now we'll key it into the calculator. We have 9.5 divided by 22.99 divided by 4. And our answer comes out to be 0.10 moles of oxygen. Now, I want you to take a moment, once you've gotten it all written down, to actually look over what we did. Any questions over what we did? How do we get 4 moles of sodium again? We got 4 moles of sodium from the balanced chemical reaction. So it is the coefficient in the balanced chemical reaction. So right here is where we got the 4 and the 1 from. Other questions? Let's look at another example. We're going to continue with that same reaction. How many grams of sodium are needed to produce 12.5 grams of sodium oxide. Just so that we have it present, I'm rewriting the equation from the previous question, just so that we can see it all together. Okay. We're going to look at what we were given. We were given 12.5 grams of sodium oxide. We're going to look at what we need to solve for. We need grams of sodium. And now we're going to figure out what conversion factors we're going to need. The first thing I notice is that we are dealing with two different substances. We've got sodium oxide and we have sodium. That means our first since we have two different substances, means we're going to need a mole-to-mole ratio, which is going to come from the balanced chemical equation. And there are 4 moles of sodium to 2 moles of Na2O, according to the coefficients of the balanced chemical equation. The next thing we're working with is we're working with grams of sodium oxide. Grams always means molar mass. So we need the molar mass of sodium oxide. We have 2 sodiums. Sodium has a mass of 22.99. We have 1 oxygen, which has a mass of 16.00. So the sodium contributes 45.98 to the overall, and the oxygen 16, to give us 61.98. So that is 61.98 grams of sodium oxide is equal to 1 mole of sodium oxide. The next thing I noticed is I want grams of sodium. Again, anytime I see grams of sodium, or anytime I see grams in general, I automatically will go to the molar mass. And sodium has a molar mass of 22.99 grams, is equal to 1 mole. Now that we've parsed out our probable conversion factors, we can begin the calculation. We'll start with the 12.5 grams of sodium oxide.
Recording in progress.
Make sure everybody is muted, please. Except when asking questions. Okay, so we have 12.5 grams of sodium oxide. The first conversion factor we're going to need to work with is going to be that of sodium oxide. So we're going to work with our second conversion factor we developed. We're going to place the 61.98 grams of sodium oxide in the denominator with the 1 mole of sodium oxide in the numerator. We place the grams in the denominator so that the unit and the substance would cancel, leaving us moles of sodium oxide. Now that we have moles of sodium oxide, we can convert from moles of sodium oxide into moles of sodium using our first conversion factor we developed. The 2 moles of sodium oxide will go into the denominator, while the 1 mole of sodium, 4 moles of sodium goes in the numerator. We place the 2 moles of sodium oxide in the denominator so that the unit and the substance would cancel, leaving us moles of sodium. But we were specifically asked for grams of sodium. So now we're going to use our last conversion factor in order to get to grams of sodium. Of that conversion factor, the mole will go in the denominator, while the 22.99 grams of sodium go in the numerator. The moles of sodium went into the denominator so that the unit and the substance would cancel out, leaving us grams of sodium, which is what we were asked to solve for. Now that we've got what we want to solve for, we can key it into the calculator. 12.5 divided by 61.98 times 4 divided by 2 times 22.99 gives us 9.27 grams of sodium. Take a moment to look at that now that you've got it all written, once you get it all written down, and ask any questions that may arise. Okay, let's look at another example. I want to make sure I'm not missing any questions. Okay. Let's look at another example then. Acetylene gas which is C2H2, undergoes combustion to form carbon dioxide and water. According to the reaction, two C2H2 plus five O2 goes to form four CO2s plus two H2O. How many grams of water can form if 113 grams of C2H2 is burned? Okay, so let's look at what we were given and what we want to solve for. We were given 113 grams of C2H2. We were asked to solve 4 grams of water. Okay, now we get to ask ourselves our questions. The first thing that I notice is that I am dealing with 2 different substances. When you have 2 different substances, it means you're going to need the mole to mole ratio. Which is going to come from the balanced chemical equation, which there are 2 moles of C2H2 to 2 moles of H2O. The next thing I notice is that I'm working with grams of C2H2. Anytime I have grams, I'm automatically going to go to the molar mass. So I need the molar mass of C2H2. I have 2 carbons at 12.01, and I have 2 hydrogens at 1.008. The carbons contribute 24.02 to the overall mass, and the hydrogens contribute 2.016 to the overall mass, for a total of 26.036. That is 26.036 grams of C2H2 is equal to 1 mole of C2H2. Finally, I notice that I need grams of water. Again, anytime I need grams, grams is going to mean I need the molar mass. So I have 2 hydrogens times 1.008, and I have 1 oxygen times 16.00. That means the hydrogens contribute 2.016 to the overall mass, and the oxygen contributes 16.00 for a total of 18.016. That is 18.016 grams of H2O2. H2O is equal to 1 mole of H2O. Now that I've pieced apart what I was given and what I wanted to solve for to identify possible conversion factors, I'm ready to key this into the start the conversion. I'm going to start with the 113 grams of C2H2. My very first conversion factor is going to need to have grams of C2H2. So I'm going to be using the molar mass of C2H2 as my first conversion factor. The 26.036 grams of C2H2 is going to go in the denominator with the 1 mole of C2H2 in the numerator. We place the grams of C2H2 in the denominator so that the unit and the substance would cancel, and we were left with moles of C2H2. Now we can convert into anything else using a mole to mole ratio. So we're going to use our first conversion factor we developed. And of that conversion factor, we're going to place the 2 moles of C2H2 in the denominator with the 2 moles of H2O in the numerator. The 2 moles of C2H2 are placed in the denominator so that the unit and the substance would cancel, leaving us moles of water. But we needed grams of water, so now we're going to use our molar mass of water. The mole portion of the molar mass is going to go in the denominator, with the gram portion going into the numerator. The mole portion went into the denominator so that the unit and the substance would cancel, leaving us grams of H2O, which is what we wanted to solve for. So now we're ready to key this into the calculator. 113 divided by 26.036 times 2 divided by 2 times 18.016 is equal to 78.192, or in other words, 78.2 grams of H2O. Now, folks, I want to introduce a new term to this at this point. Basically, I want us to take a moment to understand what this is saying before I introduce that term. What this math is implying is, in theory, 78.2 grams of H2O can be formed from 113 grams of C2H2, assuming no side reactions occur, and no loss of products occurs. Now, what I want to make note of is this term that I've highlighted, in theory. Because this is in theory, this value is referred to as the theoretical yield. Basically, the theoretical yield describes the amount of product that can be formed in theory from the reaction. So now I want to give you a moment to digest all of that, and if you have a question, please ask. Okay, let's look at another example. How many grams of acetylene react if 1.10 moles of CO2 are produced? Okay, let's look at what I was given. I was given 1.1 moles of CO2. I was asked for grams of acetylene. And just to make it where we can see it, that equation was 2 acetylenes plus 5 O2s went to form 4 CO2s plus 2 H2O. You may be able to see it, but because of my screen, I couldn't. So, okay, so let's look at this. Let's start breaking it down. We have CO2 and we have CO2 and we have C2H2. Two different substances. Mean we're going to need a mole-to-mole ratio. From the balanced chemical equation, we know that there are 2 moles of acetylene to 4 moles of CO2. The next thing I notice is that I'm starting with moles of CO2. Because I'm starting with moles, I'm going to leave that alone. Moles are we already have moles in the mole to mole ratio, so there's no need to go out and dig up a new conversion factor. We already have the conversion factor we need. The next thing I notice though is I do need grams of acetylene. And so anytime I see I need grams, my go-to is the molar mass. And we calculated this above, so I'm not going to recalculate it this time. We came up with acetylene to be 26.036. And that was equal to 1 mole. So now let's begin doing these calculations. We're going to start with what we were given, which is the 1.10 moles of CO2. We're going to need a conversion factor that has moles of CO2 in it, and so we're going to use our first conversion factor. Of that conversion factor, that in that ratio, the 2 moles of the 4 moles of CO2 will go in the denominator, while the 2 moles of C2H2 go in the numerator. We place the moles of CO2 in the denominator so that the unit and the substance would cancel, leaving us moles of acetylene. But we were asked for grams of acetylene, so we're going to have to use our second conversion factor to get there. And so of that, the gram portion will go in the numerator. With the mole portion in the denominator. The mole portion had to go in the denominator so that the unit and the substance would cancel, leaving us grams of acetylene. And because that's what we were asked to solve for, we're ready to complete this calculation. So 1.10 moles times 2 divided by 4 times 23.036 is 12.6698. And if we're keeping things according to significant digits, that would be 12.7 grams of acetylene. Take a moment, look at that, and I will answer questions. This is the process involved in stoichiometry using molar mass, mole to mole ratios, and Avogadro's number that we've been talking about for the last few weeks. The only stoichiometry that we have left besides some more of these types of problems is to actually include molarity in those calculations. So instead of continuing to hold you over today, and also I don't really have time to do another problem, I'm going to let you go for today. And on Monday, when I see you in person in class again, we will pick up with these calculations, and then I'll introduce the concept of molarity, which is what we will work with for the remainder of the semester. Just to give you a slight overview of everything coming. So when we return, we have 3 days of lecture. You will then have a 4th exam. And then we'll have 1 day where I will wrap up and answer any questions related to the final exam. And then it will be finals. So we are almost there, if you can believe it. And most of what we've covered, well, all of what we've covered, you will see in college chemistry, and in most of what we covered, you will see in the general chemistry for health sciences. Is there going to be an active homework? There is an active homework for tonight. There won't be one after tonight. So if you get it done early, you'll be done. And there won't be any, I believe there's also I appreciate that question. There's an active homework that's due tomorrow at 11:59 p.m. And on Sunday, there is a stoichiometry math chemistry ed puzzle that's due. So that's what's coming up that's due this week. Any other questions? So next week we'll continue with this and we'll start into molarity, and then we will be done for the semester. And with that, I bid thee adieu from Amarillo, and I appreciate you letting me teach this way this week so that I can actually visit with my daughter. Otherwise, I wouldn't have been able to come out here and visit. She lives too far away. So thank you, and I will see you on Monday.
Have a good one, Miss Yarberry.
You too. And I like your name.
Thanks.
The two remaining, did you have specific questions you would like to ask?